Hi guys, welcome back to 100 Days Machine Learning Crash Course. Today we want to continue our discussion about Bayesian networks, and specifically we want to talk about generative models. Generative models. Okay, so this is the topic of our today discussion. Okay. In many situations, actually, when you build your graphical probabilistic model, you want to draw samples from that graph, or from actually a probability distribution. So there are different actual techniques to draw samples from a probability distribution, but one of them that is called ancestral sampling which is relevant to graphical models. We want to talk about that a little in here. So consider a joint distribution. So when we talk about joint distribution, we mean that if we have k random variables, the joint distribution is something like this. And let's say they are related with a directed acyclic graph. So we can model them with a Bayesian network. Okay? Or in other words, each node has a higher number than any of its parents. Okay? If you don't know what does that mean, it means that if you have x1 in here and x2 and x3 in here, then you will have just this kind of connections for x3, but you don't have something like this or this for your graph. So the graph is a cyclic graph. Okay. So the goal is to draw a sample from this joint distribution. So we want to draw a sample which we call the components of that x1 hat to xk hat, and we want to obtain this sample from this joint distribution. And we know that we could factorize the joint distribution as the product for all k variables of conditional. We saw this in previous session, that we could factorize this with the conditional distribution of xk given all of the parents of the node k. So if I have x4 in here and I have x1, x2, x3 in here, then the parents are, in fact, that term will be x4 conditioned on x1, x2, and x3. So now you should know the meaning of parents, hopefully. Okay. So our goal is to draw a sample. To start do the sampling, you should start with the lowest numbered node. So if you have x1, x2, and xk in your node, you start with x1. We know that x1 is not caused by any other node, so because this is the first node, so we don't have something like this for x1. And we know that if there is a link between x1 or between x1 and other nodes, the link is something like this. not something like this. So for x1 we could do the sampling because we know its distribution. So we could do the sampling for x1. If you don't know how to sample from a distribution, don't worry about that, we will talk about that later, but just for now, let's say we know how to draw a sample from a noun distribution. So we draw a sample from this distribution, let's call that x1 hat. Then when we know the state of x1, we could actually go on, and after x1 we could sample from x2, because if you want to get some samples from x2, actually we know that we have x2 conditioned on x1, and now we know the state of x1 because it is x1 hat, so we could sample from this distribution because it is just related on x1, so we could sample from this distribution and let's call it x2 hat. So we could continue the sampling to obtain x1 hat to xk hat, and that's it. So we sample from our joint distribution by using our graph. Let's say, but sometimes maybe you just want to get some samples from x2 and x4. In other words, you just, let's say that you want the samples x2 hat and x4 hat. In these situations you could actually draw all the samples, and after that throw all of the other samples and just keep the variables that you want. So in here, after the sampling, I could just throw this away and just keep x4 hat and x2 hat to obtain sampling of this joint distribution. Okay, for practical applications of probabilistic models, it will typically be the higher numbered variables corresponding to terminal nodes of the graph that represents the observations, and lower numbered nodes corresponding to the latent variables. So what does that mean exactly? So let's say when you have a graph, typically your observed variables typically are a lot. So if you have an image and you just look at the image and vectorize that image, let's say you have your image is 60, 600 and 800, so the number of pixels in here, if you vectorize that, you will have lots of pixels, or in other words, you will have lots of terminal nodes in here. But these observed variables typically governed by some lower numbered latent variables. So for example, if you are looking at the image, so probably the important latent variables maybe are like the object that you are looking in the image, and the position, and maybe the orientation of that object. So So just by sampling from these, you could be able to obtain the joint distribution of this graph. And so typically the latent variables are low numbered in Bayesian networks. So the primary rule of latent variable is actually to allow a complicated distribution over the observed variables to be represented in terms of simpler conditional distributions. So in here we have a complex and complicated distributions in here, but we just want to model it by using some simple conditional distribution in here. For example, in here we just have object, position, and orientation. Okay. So for example, for finding position distribution in here, if you want to find the position distribution, we could actually for finding posterior distribution over objects, let's say we want to know the posterior distributions over the objects. So in that case, we can integrate over all possible positions and orientations. So we just, for finding the posterior distributions of over the objects, we could just integrate by the sum rule. We know that we could just integrate over all possible positions and orientations to actually marginalize the joint distribution to obtain the posterior distribution of objects. So the graphical model captures the causal process by which the observed data was generated. For this reason, such models are actually called generative models. So this is the reason is that this kind of graphs or this kind of Bayesian networks called graphical models. If you remember that in our polynomial regression example, we had something like this as the Bayesian model of our problem. We had noise variance in here, we had xn and w and alpha in here. So this was the graph of polynomial regression. But the point that it is not a generative model. Why? Why this is not a generative model? Because there is no actual probability distribution associated with the input variables. So in other words, for the input variables, you just consider them as, actually we just consider them as some parameters of this model, and we don't have any probability distribution for this. So, but in other words, you could not generate some synthetic data from this graph. Okay, we could actually make it generative, but by introducing a suitable prior on p of x. So if we introduce a prior for x, then we could call this graph a generative model, because in that case we could generate some new synthetic data for our purpose from this graph. Okay, so but generally, so we talked about hidden variables and or latent variables, but for probabilistic models, actually the hidden variables need not to have explicit physical interpretation. So in here we talked about the orientation, position, and object, so they had some physical interpretation for us, but it is not necessary to have some physical interpretation. It just needs to aid some modeling of complex distributions. So the point of having latent variables is to just make the complicated distributions, the modeling process of the complicated distributions more convenient and more easy. Okay, now we want to talk about discrete variables. Until now, we just talked about continuous variables. So, actually, we have, in general, we have two interesting cases for our graphs. The first one is that the parent and child node, each of them corresponding to discrete random variable. So, we could have some kind of parent and child node, and both of them have discrete random variable. The second case is that each of them corresponds to Gaussian variable. So why these two cases are so important? Because in the two cases the relationship can be extended hierarchically to construct arbitrarily complex discrete acyclic graph. So if we analyze these two simple cases, then we could generate arbitrarily complex models by just having a proper analysis on these two cases. So we begin by discrete model. Okay. So let's say the probability distribution for a single variable is P of X conditioned on mu for a single variable. And let's say this X have K possible states. For example, it could be related to one hot encoding of a vector of categorical variable. So if, for example, you have the days of the week of a week like Saturday, Sunday, Monday, and so on, you will have 7 possible states for any of your events. So let's say your first event occurred in Saturday, so you could actually encode that in with this vector. Or let's say it is occurred in Monday, so you will have something like this if you consider that as Monday, and so on. So so in this case we one hot encode the output or the X in general, and it has so K different states. In that case we had 7 different states, but in general we have K different states, and we could write this distribution as the product of k from 1 to k of mu k to x k. So in 2D, actually in two-state case, it is related to Bernoulli distribution. So if you remember that when we had Bernoulli distribution, we had something like this for a Bernoulli variable. We had this is the Bernoulli distribution. So this is so much like this, and in here we should have some constraint to make it like this. So we need to have the sum of all mu, or so the sum is 1. In here you could see that the sum of phi and 1 minus phi is 1. So and it actually makes sense. So in fact, you just in this model you just have k minus 1 parameter. So if you determine mu1 to mu k minus 1, you could determine mu k by just using this equation. Okay. Now suppose we have two discrete variables x1 and x2. Each of them has k states, and we wish to model their joint distribution. So we want to determine p of x1 and x2, and we want to do that by observing both x1k is equal to 1 and x2l is equal to 1, and by the parameters of mu kl. So because this is some kind of 2D case, and the k means that the k component of x1, and similarly for L is for x2L. So the joint distribution could be written as the product. So we have two products in here. The first one related to K, the second one related to L. Mu KL power x1k x2l, and we have constraint for k and l. The sum over k and l of mu kl is equal to 1. So in that case we have k squared minus 2 parameters for this model, right? So we have you could just easily see that we have k squared minus 1 parameters. Okay, and you could easily verify that for m variables we will have k to power m minus 1 variables for modeling the joint distribution. And actually this, we can see that this grows exponentially with m, and actually we don't like this in general. So it means that the number of parameters of our model is actually grows so quickly with increasing the number of variables, and this could complex our modeling a lot, and so it could cause some difficulty in our modeling, or cause overfitting or other problems. So, but let's see this problem. So let's factorize this by product rule. So we know that we could factorize this by writing x2 conditioned on x1 or given x1 times p of x1. So in this case, we know that we could visualize this with Bayesian network. So this is x1 and this is x2 in here. So you will have this graph. So you have k minus 1 parameter for x1, and when the state of x1 is determined, then you will have k minus 1 parameters for x2. So for each for all of the states of xk, which is k, you will have k minus 1 parameters for x2. So you will end up with k squared minus 1 as before. But the interesting point is in here. Let's say you just remove this connection. In other words, if we remove this connection, it means that the two variables are independent. In this case, we need just, in fact, the joint distribution from this graph we could write as p of x1 times p of x2. This is the actual definition of independent variables. So in this case, we just need k minus 1 parameters for x1 and k minus 1 parameters for x2. So for modeling this joint distribution, when we have independent variables, we just need two k minus 1 variables. And in general, if you have m independent variables, then you need n times k minus 1 variables. And this is so good because it linearly grows with m. Instead of having exponential growth in number of parameters by m, you just have linearly growth in number of parameters with m. So by the fact, the interesting point is in here is that by dropping links in the graph, you could reduce the number of parameters in your graph. But this is at the expense of having a restricted class of distributions. In other words, you are limited yourself to some kind of more limited class for your distribution. So this is one way to reducing the number of parameters in a graph or in Bayesian network, by just dropping some links. There are some other ways to reduce the number of parameters in graph. An alternative way to reduce the number of independent parameters in a model is by just sharing parameters, or so as a second way you could share, or it is called tying parameters. For example, in here, let's say for m variables, in normal condition we have something like this. We can arrange that all of the conditional distribution of xi given xi minus 1 for i2 to m are governed by the same set of k times k minus 1 parameters. So you will have k minus 1 just for x1, and for all of the others you will have just k times k minus 1 parameters. So the total number of parameters will be k2 minus 1 parameters for m variables. And so this is actually another way to reduce the number of parameters in a network. Another way to actually reduce the number of parameters and controlling the exponential growth in number of parameters in a model of discrete variables is to use parameterized model for the conditional distribution instead of complete tables of conditional probability values. So let's see. So let's say this is the graph, and this is y in here. So, and assume that all of the nodes are binary values. Each of the parent variable xi, so in here we have x1, x2, and xm, is governed by mu I, and so they are actually they have Bernoulli distribution, and so the mu I represents p of xi is equal to 1. So the p of y conditioned on x1 to xm requires 2 to the power of m parameters to represent actual p of y is equal to 1, because for each state you need to analyze this and setting of the parent variables. So you need to power m number of parameters in here, and we will see that we actually see that in here we have exponentially growth in number of parameters with m, but we can reduce this by using logistic sigmoid. So we actually have seen sigmoid in previous sessions, but in here you could model p of y is equal to 1 conditioned on x1 to xm by applying sigmoid of w0 sum from I from 1 to m of wi xi, which you could write as w transpose x. And in this actual equation, if you forget what is sigmoid, the sigmoid definition is 1 over 1 plus exponential of minus a, and the x is x null to xm transpose. So this is this has m plus 1 variable with an additional x null in here, which is actually clamped to 1. So you could see that we could see this as w null times 1 and call this x null in here and concatenate all of the x's together to have more compact way for writing this. And we have also m plus 1 parameters in here for w, and so as you could see in here now, we just have m plus 1 parameters for w, m plus 1 parameters for x. So we have 2 m plus 1 parameters in general. And so as you could see, now we have linearly growth number of parameters. So we have linear growth in number of parameters. So this is so cool that we could control the exponential growth of number of parameters different ways in graphs. And so this is actually the analysis of discrete case. And in the next session we actually continue this discussion to continuous variables and try to start Markov random fields. For working with Bayesian networks, you could there are actually lots of packages to work with Bayesian networks. You could search for them, but maybe the more important aspects of Bayesian networks to get some insights about some graphical models, because maybe you could relate this after learning the Bayesian networks when we talk about neural networks or deep learning. Maybe you could relate this with Bayesian networks, or want to research on the relation, or getting some new ideas about relating Bayesian networks to deep convolutional neural networks and so on. So maybe the Bayesian networks themselves are not so much practical for you as a data scientist in here, but they actually could improve your insights about probabilistic models and other models and other probabilistic models. So I hope that you enjoyed from this session and try to actually practice previous topics that you learned, such as normalizing or PCA or with SVM and so on, to just get hands-on on practical applications. So we continue this discussion in the next sessions. Hope to see you in the next session. Bye.